welcome everybody. I'm Filippo from Naples, and let's say the story I will tell today, it's about the way we do photonic circuits. I mean, we heard in the first talk why an example of why they're useful. So I hope I will, convince you that there are few approaches which are interesting to make them. So let me start with a brief introduction on photonic circuits. So typically in a photonic circuit, you have a bunch of input optical modes. You have a bunch of output modes. They may be the same ones, different ones. The key point is that they are connected in a network. And if you take a mode at the output, this is typically given by a superposition of the input modes, and these are all weighted with the entry values of a matrix. This matrix is not necessarily unitary because some light may be scattered out of the system, and this, for instance, enabled very recently to build this kind of it's a meta structure in which you have 3 input modes, 3 output modes, and the way you shape the height of this silicon slab enable you to implement a matrix vector multiplication. Just by controlling light which is going out, light which is remaining in the system, you can precisely implement this operation. But in the remaining of the talk, I will focus on unitary operations. So essentially, all light remains in your circuit. The typical way you implement photonic circuits is with integrated photonics. So Zeilinger came out 30 years ago, more or less, with this very powerful scheme where you decompose your unitary into beam splitters and phase shifters. And essentially, in this way, you are universal. There is a recipe, you can build your circuit, and you can realize any unitary in this Hilbert space. So now technology is very mature. You can do this with waveguides in glass or with silicon waveguides. And this is just an example of a very nice application of this concept. But the story I will tell you today is not about this very standard approach to photonic circuits, but there is another possibility. You can use spatial modes of light and other kind of system, not integrated waveguides, to do the same task. So this is a very nice picture from this paper by Meul Malik group in 2024. On the left, you find the standard approach. So the unitary is built as beam splitters and phase shifters. But there are at least these other 2 ways. The one to the right has been also introduced in the first talk, is MPLC multiplane light conversion. You have different planes where you do just phase manipulation, and if you combine this with diffraction, you can implement on spatial modes any unitary operation. And then there is this other very nice approach here. I have a slide here. It's based on this paper in 2020, Sylvain Gigan group in Paris, and they essentially demonstrated that with a complex medium like a multimode fiber, combined with the phase manipulation, you can again implement any unitary. So here to the left, here is the MPLC in Robert Fickler group in 2020. This is Sylvain approach. And I'm mentioning also this, which is not with the spatial mode, so it's with time beams, ultrafine time beams in Canada. But just to mention that there is a variety of approaches you can take to implement these operations on optical modes. So not only integrated waveguides. But our group, in my PhD, I've been working with Lorenzo Marrucci in Naples, so our specialty is using spatial modes. And so we, starting from 2015, we started to realize this kind of circuit with orbital angular momentum modes. So we did a few works, especially focusing on topological physics. But then we were kind of unhappy that the modes we were using were arranged on a 1D lattice. So we wanted to find out a way to go into a 2D lattice. And to do so, we changed our encoding scheme. So instead of using orbital angular momentum modes like this, they are essentially labeled by an integer, only 1. We moved to a much simpler basis, which is a momentum basis. So you take one mode, which is like this, then you take a family of modes that you obtain by tilting this plane wave, essentially this Gaussian beam, into the x and y directions. And this way, you can realize a 2D lattice of modes that you can address and you can couple to implement your circuit. Now, the main point is how you're going to couple these modes. So what is our way to take a mode and couple it to the neighboring ones, for instance? So we are specialized in fabricating these liquid crystal devices. This is just a nice picture, a nice sketch of it. So you have essentially a very thin slab of 2 glass plates. In the middle, you have a thin layer of liquid crystals that we can pattern arbitrarily, so we can create this structure. And in particular, these plates we are using for these circuits at the beginning were gratings. So you see that the angles of liquid crystals are varying linearly in one Cartesian direction. So in this case, it's the x, and the period is lambda, capital lambda. So this plays a role. I will tell you what is the role in a minute. Because if you take one of the modes, so just take the first Gaussian beam, and you want to couple it to the neighboring ones, you go through one of these devices, and these are giving momentum kicks. So you can give a momentum kick to the left or to the right, and you give the right kick if lambda is essentially 2 pi over the kick that you want to give. So we pick the modes we want, their separation in k-space, and we fabricate the right components giving the right momentum kicks. And so essentially the photonic circuit is just a sequence of these elements, more or less. I'm making the story short because there is no time, but essentially that's it, just a sequence of devices. And you see, this is a numerical simulation. In the output, you put a lens. All these modes, these tilted modes, become spots in the focal plane, and you can read them out, and they form a lattice like this. So the first experiment was in 2020, and this is how a setup looks like. All these wires are because we can control with an electric field the overall birefringence, and this is very important because you can pick values which make these plates transparent. So you can also implement the identity transformation if you pick the right voltages, or you can tune them to do what you want. And this is how one of these devices looks like. You can see the pattern only if you put them between cross polarizers. This is a cubelet, it's not a grating, so it's a linear, in azimuthal gradient, but you can just unwrap them and you create our G-plates. So now let me come to the latest results, which are about programmable and high-dimensional circuit. So let's focus on the high-dimensional part first. The circuit we're implementing, the unitaries, are quantum walks. So quantum walks are very simple toy models for quantum dynamics, and essentially they describe the dynamics of a particle starting from a lattice and spreading through the modes of this lattice in a controlled way, so with a given unitary evolution or a given Hamiltonian. And typically what you do in quantum walks, you start with the localized mode, and you have the final state, which is spread across lattice sites, and you read them their intensity. So the circuit, the map we are implementing is just a quantum walk. It's something like this. So we start with an input mode, and we get to the output modes with the quantum walk dynamics. So the results I will show you are about these dynamics. Now the point, what is the point? Let me go back here. If you want to scale to go to high-dimensional systems, so high-dimensional means a large number of these modes here. In order to couple them, you have to cascade many devices. So the number of devices you have to put more or less scales linearly with the number of modes you want to have at your output. And so if you input a lot of devices, you're going to face issues with the transmittance, because if you take the transmittance of a single device, which is t, after n devices, you will get t to the n. And so even if t is 90%, I mean, you clearly realize that after a few of them, your efficiency will drop. So we were kind of asking ourselves, is there a way to compress all these into a few plates? So let's say you take all these. Is the optical transformation performed by this bunch of plates equivalent to maybe just one or to a few of these plates? And we found in 2023 that there is a way, it's not universal, so you cannot squeeze all possible unitary maps, essentially only those related to quantum walks which are translational invariant. But if this translation invariance holds, which is, I mean, typical in many tight binding Hamiltonians, for instance, you can squeeze the transformation into just 3 plates. Of course, the pattern you will have on these plates is much, much more complex than the standard grating, the linear grating we showed earlier. But, I mean, it's possible. And then the setup is like this. I mean, you just take a Gaussian beam, quite large, you pass it through these plates. This must be very close to each other, and you go to a camera in the focal plane of a lens, and you read the power. So we did in 2023 the 1D version. We managed to have distributions which are equivalent to 240 time steps. I mean, this is just an example. And here, a single input mode was coupled in a controlled way for more than 400 modes. And then more recently in 2025, we published the 2D case, which has subtleties. I cannot go into the details, but anyway, this is the pattern you have just in an instance of these plates. And this is this is an experimental image. So the distribution of spots you have in the focal plane. Now let me go to the final part, which is the programmable part. So this has been already published, but how to program this? So let me go back here. These plates are static. So once you fabricate them, the pattern is that. If you want to change the unitary, you have some tunability. In the last paper, we show that what are the unitaries you can implement by changing the voltage you apply to these cells, and this gives you some tunability, but the pattern is static. If you want to change completely the unitary, you have to change the plates. So we wanted to realize something which is programmable. So you have your setup, the setup is there, you change remotely some parameters and you change the unitary without the need of changing the setup. And to do so, we replaced our liquid crystal devices with spatial light modulators. A spatial light modulator is a commercial device. It's something like this. This is just one example. Is made by pixels. It's a liquid crystal device, so you have liquid crystals like in our plates, and in each pixel you can control the voltage essentially. And by controlling the voltage at every pixel, you can implement a phase mask. These are normally used to do phase modulation of light beams, but if you take 3 of them, like in the first case, and between consecutive SLMs, you put an halfway plate, so you change polarization, we demonstrated now in this paper that you can do the same thing. So essentially, really the same thing we did with our liquid crystal devices, but now in a programmable way. So you just go to your computer, you change the holograms. So this is not working. Anyway, that's okay. There was the animation also for the 1D case, but anyway, you just change the holograms and you change the transformation you're implementing. And so you are programmable now. And this is very nice for us. Oh, it's blurred. I don't know why. But anyway, a thing we are a bit puzzled with is that the similarity is going down. I mean, we are expecting that the similarity is the classical fidelity between the target and our distribution. The experimental one is dropping, and we think, we're quite sure that this is due to the bad resolution of the last SLM. It's just practical. But anyway, we are able to see the typical feature you see in these quantum walks, the ballistic spread of your wave packet. Then in the final part of this experiment, we did everything quantum. So we sent one photon through our system. We have SPDC, so 2 photons emitted here. One is going through the system. The other one is going to a single photon camera. This is a time stamping camera. We can give tags, temporal tags to the arrival time, to the photons arriving there. And we can do the experiment recording output states like this. These are states recorded on these cameras. These are photons hitting the camera at different positions. And these are the experimental measurements we obtained with these single photon states. So I'm going to my conclusions. Time is over. If you want to know more about what we are doing in these things, there are 2 posters about our PhD students. SNEA is presenting, I've announced earlier that these are not universal machines. So to go towards universal machines, we are using these plates to do liquid multiplane light converters. SNEA is presenting them. And Paola is presenting how to use this kind of approach to implement non-unitary and non-emission dynamics. So if you are curious, you can go to their posters and talk to them. So now let me thank Professor Karimi in Canada, who hosted Mary, our PhD student, to do this experiment. And this was funded by these grants. Okay, this is our group. This is a nice picture in Naples. So this is Capri. This is the castle here. And this is our group. There are PhD positions open now. The selection is ongoing. So if you are interested or you know someone who's interested, you can go to our website or you can contact me. And with this, I'm done. So thank you very much.
Thank you very much. There's time for one quick question. Alex.
Did you think about sending 2 photons into your circuit rather than 1 photon?
This is the thing we are doing at the moment. So, I mean, in this experiment, we on purpose decided to have only 1 photon going through and do the heralding thing. Now we are sending both of them. We are using the timepiece camera to record the events, and so we are building either both this system and the more universal one with 2 photon states going through to see also 2 photon interferences.
Okay, thank you very much.
You're
we
welcome.
have to go on. So let's thank the speaker again.